So how many of you are from, like, you are in first year or second year? Only one. Okay, quite a few. Let me know when I should start.
5 minutes. Sir, we can start.
Okay, so first of all, I should thank the organizers for organizing this and also inviting me to give this lecture. It's always a very pleasant experience to be here. Before this, coming to this lecture hall, I was thinking about this. I was not so keen on getting it recorded, and the excuse I had was this. You know of two-slit experiment, right? So a photon. Now this guy is hitting that screen. There is an observer, right? It can take any of these paths. It's in superposition of those. But if you start observing it, you'll find it in one of those paths. You'll force it. So in general, this kind of lecture, because it's a lecture, not a talk, right? It's not a performance, it's a lecture. It will be in superposition of two things. Me telling you and learning something from you. But since there is a camera observing you, it forced to one of it. Okay? So it changes, the dynamics changes a bit. But still, nevertheless, I will encourage you ask, and I will try to hide my ignorance as much as I can. So, even if you have not studied or not done a loop calculation before, whatever I say should be accessible. Okay, so that's not a pre-requirement. So do not worry about not knowing something already. So let's begin by connecting with what Saurav was telling us. So he talked about threshold. Imagine you are looking at a scattering, okay, let's say at LHC or Tevatron or wherever, and you pump energy barely enough that final state is produced. Then whatever else is produced, it has to be because you are doing quantum field theory, these other processes will happen. So you will have all this radiation coming out, and it will be forced to carry zero momentum because what you have pumped in is barely enough to produce that final state. Is that okay? And since that radiation that is going out is soft, and the matrix elements are going to be singular, as you have seen in the previous case, okay? Because soft gluons or fermions, they will bring in singularity. What you are looking at, so if you are asking what's the cross section for producing a Higgs in the final state when you are at the threshold, that's Z minus one thing, right? That's what he was describing. Then quantum field theory, perturbation theory is going to give you a result that does not make sense. Okay, it's going to be singular. It's going to be singular order by order. Okay, so it looks like you do not have predictive power, but because you are, let's say instead of Z, I could think of Higgs distribution and could think of, okay, this is of PT square, that's PT or PT square. Your fixed order computation will give you something similar. Okay, I've just changed from threshold to PT because I'm more used to drawing that one. But the real result in detector is not infinite. That's something finite. Okay, so even though your perturbation theory is not making sense in this region order by order, the physical observable that you should actually construct by summing up all the terms to all orders in perturbation theory is a meaningful thing and is what is going to match with the experiment. Is this point we agree on? Okay, so order by order they are all going to be very large. So the logs he was talking about, they are going to appear at every order, but there will be a pattern in which they will appear and that pattern allows for that resummation. And the reason behind that pattern is the fact that that radiation factorizes from the hard scattering. Okay? So we want to learn those techniques which will allow us to do factorization, because once I can factor out this soft radiation or the collinear radiation which gives all the singularities, I can use the renormalization group techniques to sum them up. Okay? So that's the goal. But today what I will do is I will start talking about something very simple which will lead us to that goal, because when you calculate all these objects, you are going to be calculating Feynman diagrams, right? These Feynman diagrams are going to become singular because of certain configurations in the loop momentum, where the loop momentum becomes soft or collinear, right? We want to know what kind of singularities appear and when do they appear. Okay? And if I can develop tools to deal with these to all orders in perturbation theory, meaning no matter at what loop you are looking at, you are able to tell which configurations are going to be singular and what form they will take, my hope of succeeding in factorization can be realized. Is the goal okay? We are on the same page? So that's what I am going to do. I am going to look at Feynman integrals. And even simpler, I'll just look at integrals. Okay? Feynman integrals are complicated things. So I'll just look at integrals in complex plane for one variable. Okay? That's the simplest thing we can do. That's the toy thing, but with very important learnings, and that we will utilize later. Okay? So for now, you could think that I'm not doing any physics. I'm just doing some complex analysis. Okay, so singularities of complex functions defined as integrals. So I'll have some function which is defined by an integral which I want to analyze. Okay? So think of a function f of some variable z, where z is complex. This z is the equivalent of your external momenta when we start looking at Feynman integrals, right? And z is a complex variable. So when I look at Feynman diagrams and the external momenta, I will be taking external momenta as complex, okay, and study in general. So f of z is some integral over variable omega of a function phi which depends on omega and z. Okay? And this integral you do over some contour in the omega plane. So that's your complex plane omega. That's some contour that you take from some place to some place, that's gamma, and it is over this contour you do the integral of the integrand phi, which depends on z, and that's why you get the function f of z. Is that okay? Now, typically such an integral would exist, right? It's a contour integral, that's some complex number. The magnitude of that complex number is less than or equal to the magnitude of the integrand times the length of the curve. Remember this expression? Okay. So that would exist. There is no reason why it will not, unless it so happens that the integrand is singular, right? So if a pole, for example, were to sit on the contour, then the integral does not exist. It's not defined. So let's imagine that this function phi has poles at certain locations, and these are those locations, and the poles will of course depend on that and the variable z. some number of poles, okay, in the omega plane. So you choose some value of z. This is, let's say this is a integrand which has the form of a rational function, like you will have in the case of Feynman integrals, okay, and the denominator will be 0 at certain locations, and those are the locations. So these are the poles, and they are located at certain places. Okay. And as you change z, these poles will move. Okay, you change the value of z. Since this is a function of z, it might migrate to somewhere here. This might go somewhere else. This might go somewhere else. Okay. So as you change the value of z, you can find the integral. There is no issue. There is potentially an issue if this or any of the poles or many of the poles were to migrate and land up on the contour. Then your integral is not defined. Is that okay? So as you are changing z, these poles are moving around, and maybe they land up on the contour of integration. But that may or may not be a problem, depending on whether you have the freedom to move the contour away. Right? See, the result of this contour integration in this configuration, where the poles are sitting here, is the same as the result of this contour integration. Right? If you were to integrate over that contour, you get the same result, or this one, same result. Suppose your pole reaches here, is going to reach there for some value of z. You already arrange this guy to take this shape, and it reaches there, but your contour is not there anymore. So no problem. Is that okay? That's the analytic continuation that you are providing, okay, by deforming the contour. So typically you think like this, that this pole is coming and it's about to hit this, but you can deform the contour. Okay? If it is still reaching, you can deform the contour. No, you don't have to.
You don't have to.
No. So if you close the contour and there are no poles inside, that contour integral is 0. What I'm saying, but these two facts are related. What you're thinking and what I'm saying, they are related. It's that if you are able, I mean, the result, the contour integral, does not depend on the endpoints. I mean, does not depend on the shape of the contour as long as your endpoints are fixed. It depends only on the choice of endpoints. If the function is analytic within that entire region where you are deforming the contour. Is that okay?
All those are not analytic.
Pole is a pole. Function is analytic. Pole, there's nothing like pole is not analytic. There is a pole. There is some pole.
The vicinity of the pole, the vicinity to the pole, what is the functional behavior there?
Yeah, that's the entire lecture about what the function would be about. What kind of function, what kind of behavior the function would have. We'll come to that. That's what.
For every like z, your pole will be moving. So accordingly, you will be deforming your contour every time.
Yeah.
Is it correct?
Yeah. Any other question? So the procedure is clear, right? If the pole was one of them or any number of them were going to hit here, and that's the contour you are starting with, you already deform it, no problem. Now that guy doesn't land there. Or you say, okay, when it is coming, I will deform. Right? So as long as you have the freedom to deform your contour, your function is going to be an analytic function. That f of z will be an analytic function. Okay? The problem would be if that freedom of deformation is not there. And we are interested in those cases. Okay? Because that is going to tell you where the function is not going to be analytic. And we'll be figuring out what kind of singularity structure it would have.
poles could be multivalued as well.
Poles should be.
I mean, is this phi a rational function?
Yeah, I'm imagining rational function because I'm going to look at Feynman integrals. They will have that kind of.
But Feynman integrals are not always rationalizable, right? In some sense, in some case, the square roots cannot be infinite.
No. So you take all. See when we do the loop integral, you'll have all these propagators which will have of the form, let's say 1 over q square minus m square. Q is the momentum flowing there. Q will be composed of the loop momentum and other external momentum. You use Feynman parameters and then form a square and raised to the power n. So that's the kind of general structure you would have.
Sir, what if one of the pole goes to the end point?
Okay, so what's your name? Shubham. Shubham says, what if one of the poles goes to the end point? That is what we call end point singularity. Okay, because you cannot deform your contour. So that is one of those cases where you will not have, you cannot provide an analytic continuation because your pole has reached the end point, and end point you cannot move because these end points are fixed, right? So that's the one location where this integral would be singular. Okay, and as we note here, that's what is called end point singularity. So I'll take up an example and try to see how it works. So let's do it there. So let's take, so I'm following a review that I have written with Nilima, Lorenzo and Chiara, and I'll just give you the reference. Okay, this is in Physics Reports. Volume 994, 52023. Okay, you will also find it on the archive, so you can, and also you can use and look at the references given in this report. Okay, so let's take up a simple example. Okay, that's a simple thing. You have the integrand has a pole at w equal to z in the omega plane. Okay, so let's draw it here. And your integration contour is from 0 to 1. Okay, and that's the direction of contour. Okay, let's make it a little bigger. And where is the pole? Pole is at z. So here is your z plane. You choose some value of z. Accordingly, you'll have a pole at the same value of omega here. So let's say you choose a point in this z plane. Correspondingly, you have a pole in the omega plane. Okay, the poles I will mark as cross. Now, if z approaches the real axis, let's say so if you evaluate the integral for this value of z, you have an analytic function. For this one, analytic function, if it goes there, analytic function, because your pole is going like this. But when it hits here, you can always deform your contour, right? So there is no problem; it's still analytic, correct? As we discussed earlier. But now if instead this guy is going there, then this pole is migrating here, and you have endpoint singularity. Now you have a singularity, but what you want to know is what kind of singularity you have. Okay, so what I will do is I will take the point Z, I will take this point, okay, and I will make a complete circle around it and reach back to the same point and see what happens. Is that okay? No problem, right? I'm just taking different values of Z and I come back to the same point. My function is changing its values, and then let's see what happens when Z comes back, right? An expectation, a naive expectation could be that because you have come back to the original point, the value of the function is the same after you have completed your full circle. That could be our expectation, right? So let's see what happens. And whatever I say for Z equal to 0 would be applicable for Z equal to 1, because this guy could migrate there, okay, and it will be the same kind of analysis. Okay, so let's look at this Z plane and the W plane, okay, and here your contour runs from 0 to 1. So let's start in the Z plane, a point here, and come back to there. Come here, okay, then I will make the full circle. So corresponding to this point Z, since omega equal to Z is the location where the pole is, I have my pole here, okay, and as I go like this starts moving like this, but instead of making it land on the contour, I start deforming the contour. I do it like this, and then next time like this, okay, and I keep deforming like this. Okay, it's not here, okay, it's just deformed like this, and it reaches, okay. So from origin your contour starts, it goes this way, and see. Is that fine? Now let's take it further, bring it here. So it was initially started here, and it again reaches this place. Okay, so I have been deforming and I have reached this location. But now what I can do is, okay, I come like this, and then I go like that, and here it is like this, and here is your pole. You have come back here, okay. So you see, in completing the circle, after I've completed the entire, I've made a loop around this, then the pole which started from here has come back to the same location, and this is equal to, so you can see these dashed lines, they are sitting on top of each other. So that's the contour going this way and the backwards, so they are related by minus sign and they cancel. That's why I am able to do this. This thing forms a circle, okay. So I have a pole in that circle, and if I cut that, this thing can be shrunk back to this location. Is this clear? So what you have is 0 to 1, the contour is again from here to there, plus that. So in circling around once, okay, and coming back to the same location, you have the result that you have is the same integration over the contour plus an additional piece, okay. That's the residue that you have picked up from that pole. So you see your function f1 of z does not have the same value as it had for the value of z when it was here. After making a full circle where theta has changed by 2 pi, your function value has now increased or decreased or whatever by 2 pi I times the residue of this pole. Agreed? Now you make one circle again. So you have reached from there to here, you make one more circle. What happens? Everything repeats. You again pick up a residue.
I think that you know that f1 of z, you have one value, and then you have f2 of, let's say the right z is e power I pi
R into the theta.
and then pi, if I shift to pi plus 2 pi,
2 pi.
it will pick up one.
It will pick up that thing. Yeah. It will pick up this 2 pi I times the residue.
That's what you're saying.
That's what I am showing here. Yes. Is the claim clear? Okay. So the value of the function has changed by a particular amount. That amount is 2 pi I times the residue. If I now again make a circle, so I made one circle, I make once more. The value of the function again changes by 2 pi I times the same residue. Okay. One more time the same thing. So no matter how many times you do it, every time you pick up the same value. So your function keeps changing. Do you by the same amounts? Does that ring a bell?
Branch cuts.
Okay, something more? Yeah, in the right direction.
Arithmetic progression.
Now we are thinking of, you say something about the analytic function f of z, right? It's multivariate. Of course, correct. Okay.
It's binding.
Yeah, these are. So what we are seeing is the function is multivalued, of course, okay, but the change, okay, you know, if you have a branch point and you circle around it, when you have completed a circle, the value of the function changes, right? For logarithmic functions, that change is always the same no matter how many times you do this, right? So let's say you go around it once, there is a change in the value. If you do it once more, the change in the value and whatever new value you get is again the change, the amount of change is the same as the previous one, and that's what you are here seeing, right? So what do you expect of f1 of z? You expect it to be a log. Do you see the log now? You know how to integrate this. You always knew how to integrate that, right? So the function, so you see I didn't integrate it for you. I didn't do the integral and then say something. What I have done is I have done an analysis of how the poles are moving around in the complex plane W, and from there I infer that because the discontinuity in crossing that, okay, let's not make that connection, but that connection you should make. The discontinuity that you have in the value of these functions, it is equal, okay, so that has to be logarithmic function. That much I have been able to argue. And now let's look at the result.
Omega minus z whole square, then it's not, I mean, if we integrate it out, then it's not logarithmic.
Yeah, so in this case I am claiming logarithmic.
Yeah, because this is the single pole.
That's a single pole. What will happen for a double pole? We'll figure out. Okay. It may not change by equal values. I don't remember. It's not on top of my head. So this is, yeah, maybe I'll just write here since I've already written f1 of r e to the I theta plus 2 pi or 2k pi. Let's put that. Okay, that's the z I'm choosing is equal to f1 of z plus 2 pi I or minus 2 pi I times the residue. Okay, that's something I have shown you. So if you agree to this, then the same thing can be repeated for that, because your pole could migrate to z equal to 1, and everything what I said goes through. And again you realize that if you make the point z, if you make a circle around z equal to 1 in the z plane, okay, then again you will start picking up 2 pi I times the residue of the poles there. Okay, so again there will be a logarithmic branch point at z equal to 1. So what we learn is we have 2 branch points, both are logarithmic, one is at z equal to 0, one is at z equal to 1. Is that okay? Claim is fine. And here is the result. It's log of one branch point is at z equal to 0, another one is at z equal to 1.
Start from 2 and go a circle around, then we won't pick up another residue.
Say again. Say.
So if R, let's say, more than 1, if we start from just 2, and then if we go around, it won't pick up another
No.
residue. Should that not?
That's correct. That's absolutely correct. So that's 0. So I'm in omega plane. That's omega equal to 1. And in the z plane, let's say you start from here, you come back here. Okay, you have enclosed. So when you do that, this guy will do exactly that thing here, right? Because remember the pole is omega equal to z. So it has encircled both of these. My contour is here. My contour is never requiring any deformation, and it's not going to get pinched at either this place or that place. See here, because of this thing, right, the end point moving here, I had this issue. That is not going to happen here, right? And which is something you know already. If you encircle both the branch points, your function value does not change. You are on the same sheet. Is that fine? So it will be on the same sheet. It will not change. It will be a single valued function. Or either, so you started from here, or let's say here, and you came back to that point. This is what happened, and it didn't change. Or you could do another thing. That's 0 to 1. You could start here, corresponding value in z, and you do this. Again, it does not change. So just making a loop does not change the value. You have to encircle the end point, okay, or correspondingly. And that end point will give you a branch point. So what we saw here in this example is we got a logarithmic branch point. Any other way in which my ability to deform the contour goes away? Two poles are pinching on the contour, right? That will be another way. A piece of cloth would be better, no? This leaves behind all this white thing. Okay, so that was endpoint singularity. So this is one example which tells you of this other possibility. So we are in omega plane. That's the contour from 0 to 1. And imagine that the integrand is such that you have one pole somewhere which is fixed. It doesn't move. That's a fixed pole. So you could have 1 over omega minus a. Okay, so a is a, it's a fixed number, so that's there always. And then you could have another pole, let's say, situated at omega equal to z, right? So that's, and this guy, as you change z, it moves around. And there might be a situation. So what you could do is this: you take it here and you deform it, and then you take it further, you deform it further. Okay, whichever way. Then you go further, you deform it further, and eventually it will hit there. And there's no way you can deform. Now your pole is sitting on the contour. Now your integral is going to be singular, right? It's not defined, it's singular. And you want to again know about the nature of singularity. Right? Earlier we saw we have a branch point, logarithmic branch point. What kind of singularity you get in this case? Okay, is it clear? So we want to look at an example of this kind of situation. So this integral from 0 to 1 okay, let's also assume some values of a which will be helpful in creating the argument that I want to. So that's the problem defined for us. Okay, so a contour running from 0 to 1, that's a pole at a, that's some point z in the z plane that corresponds to the pole here, and a values lie from 1 to 2. Okay, and 1 or 2, 1 is not included. Hmm? This was an example where, in that case, yes, but in the problem that I am giving, a sits on the real axis. Here. But whatever I say here, it's true there. It could have been there also, no problem. Okay, so clearly, if z were to approach 0, then this pole will approach the endpoint here. Or if it were to approach 1, it will. So those singularities are present anyway. Those endpoint singularities are present, meaning the f1 of z has two branch points, one at z equal to 0 and another one at z equal to 1. They are there. Okay. Now I want to see what's the effect of this thing here. So that's an additional feature that we are going to see now. And there is something very nice and cool and unintuitive which is going to happen. Yeah, you can do, but we want to see, it's fine, I mean, whichever way you get. In fact, you can see what I'm trying to do is not do the integral and then make some remarks. Without doing integral, what the poles are doing, when they pinch, how they pinch, and what kind of singularity you expect, that's what I'm doing, right? Just like there, I did not give you this one and then said, look, these are the places where the branch points are. Okay, so let's look at this. I just realized that I have issue with this not being very clean. So I'm searching for a cloth with which I can remove that.
You can use whiteboard.
No, I have issue with that also. It's okay, don't worry. So, okay, let's start with. I have a contour running from 0 to 1, okay? What I want to do. Just a second before I, yeah, poles have written. Now also I should draw the z plane. Okay, and remember I have told already that there is a branch point here and a branch point there because of that thing. Okay. Yes. Sorry, someone said something here.
It is a function of z comma a because only w is getting.
See, once a is fixed, it's not a function of it, right? But if you want to say I can change a, then yes. So for me right now it's a fixed thing. There is only theta. Okay, so that's the z plane. Those are the branch points. Let's sit on the principal sheet of the function f1 defined by these branch points, right? So you have a cut here, okay, and you're sitting on the first sheet, and there is no issue. You can evaluate for, you can whatever evaluation you do, there is no pinching, nothing happening other than those ones, and you have analytic function, right? But now let's look at this. Now I'll make a loop around this. So I'll just write it on here. So let us take a point z equal to z naught, some point you take in the z plane, which is not equal to a or 0 or 1, and take it on the principal sheet. Okay. Now the function is analytic, as I have already claimed. Okay. Now I'll make a closed circuit around z equal to 1. So I'm going to make a circuit around z equal to 1. So let's start with point A here, which corresponds to this, and start making a circle around this and come back to here. Okay. So as I move it here, it goes like this, but no problem, I can deform the contour. So as you are deforming the contour and you come back, since you cross this branch cut, after making the full circle, you are sitting on the second sheet, not the first sheet. You agree to that? Because your function, I told you already, because of this factor, you already have 2 branch points and there is a cut here. Okay. Let me go through. So there is a cut here for the function, that much I know. I start from a point on the principal sheet, all is good here, no problem. I start going this way, which corresponds to going this way, which means at some point I'm going to cross the cut here, but that's not a problem. I can drag the contour, but the contour at the end gets pinched when I reach again z equal to a on the second sheet. Is that fine? So I have a pinching not on the first sheet. There is nothing, no problem. The integral is well defined. But on the second sheet, you have a pinching that is happening, and contour cannot be deformed, which means your function is going to develop a singularity not on the principal branch, principal sheet, but on second sheet and third sheet and other sheets. Is that point clear? So if you agree to that, let's write down the result of this expression, this integral, and from that integral we see that whatever I have told you is indeed true. But you agree to the picture, right? You see that the pinching happens on the second sheet, not on the principal sheet. So an explicit integral, which is something Weber wanted to do, okay, you can do partial fractioning or whatever you like, you get this. Who was suggesting partial fractioning? Okay, Saurav, exercise for you. Okay, there is a 1 over z minus a, looks like a pole at z equal to a. So let's look at the principal sheet. Okay, principal sheet. This seemingly a factor that is going to give you a pole is actually regulated by this factor. As z goes to a, there is z minus, sorry, did I write this? A z minus 1 z a minus 1, yeah. So it will be a minus 1, this is also a minus 1, and that just gives you a factor of 0, which kills that one, right, log of 1. There is a z. I think I am writing it so wrong that now it's fine. A z minus 1, z a minus 1, right? So when z equal to a, that becomes a minus 1, that's a minus 1, that cancels, z cancels with a, log of 1, okay, and that's why there is no pole on the principal sheet. But now you take z on the second sheet. You have made a full circle. Log will not be real now, right? Log will have an I pi thing. That factor, the imaginary part, will multiply with this 1 over z minus a, and then your function has a pole, right? So my claim that, or whatever I showed here, can be also seen here. Is that okay? Not happy? No. Saurav?
Can you repeat last time?
Yeah. So, which part I mean, or everything, whatever I said. So I am saying that's the result of integration. There is an overall factor 1 over z minus a. Looks like there is a pole, right? But I claim that there is no additional singularities if you are sitting on the principal sheet defined by these two branch points coming from this pinching, right? Because your pole is sitting there, integral is defined, there is no issue. But when I write this way, it looks like there is a pole. All I am saying is, when you put z equal to a, and where z is sitting on the principal sheet, okay, you have not made a circle, then this thing gives you log of 1, or in the limit that gives you 0, and that kills this one. Okay, but if you go to the second sheet, okay, there is imaginary contribution. That imaginary contribution multiplies with 1 over z minus a, and you have a pole, which is what I argued from here, that you have a singularity. Okay. So these are two ways in which your contour can get trapped and give a singularity. One is endpoint singularity coming from the endpoints. Another is two poles forcing the trapping the contour. You have any other possibility? Anything else that can happen? Okay, let's then do that one. So what I am going to describe is the following. What can happen is, you are avoiding some pole because you are moving z and your contour is, you need to deform. Okay, that's fine, you deform it, there is no issue. But imagine you have to deform it so much, or rather you have to deform it infinitely, that your contour becomes infinitely long. Then that mod of f of z dz, which I said that this number is less than f of modulus of f of z times L, where L is the length of the contour, that's L is going to infinity now, right? So if your pole migrates and drags along with it your contour to infinity, then you are going to have another singularity. Okay, that's what I'm going to give you an example of that one. So I'll give you an integral which has this feature, and it can be a homework to, or even here you can see directly that you see that indeed the contour is getting dragged to infinity, but it will be very easy to just do a change of variable, okay, by an inversion, and then do the integral, and then see the same feature. Instead of at infinity, you see at z equal to 0. Is that okay? I can map infinity to 0. So that's the third variety. How are we doing with time? 5 minutes, right? 10 minutes. Okay. So let's look at the integral f3z Okay, so where are the poles located in the omega plane? Can anyone help? There is only one pole, and it is located at -1 over z. And this is what I'm doing. I'm doing the integral from 1 to a. So let's change the variable and define y equal to 1 over omega. Okay, so d omega is minus 1 over y square dy. That's just simple thing, and the integral f3 of z becomes, you can do it with me, 1 over y times y plus z dy, and the limits are from 1 over a to 1. So in the y plane, so after a change of variable, I have done an inversion from y to 1 over omega. Now I should look at what is happening in the y plane. You have a pole at y equal to 0, and you have a contour running from 1 over a to 1. That's what we have now. Is that okay? So that's the same situation we had before in the previous example, right? You had a pole sitting at z equal to 1. See, these are the limits of that contour, and then you have another pole sitting there. So your contour is going to get trapped here. Remember here, it's the same thing, right? You had a contour, then a fixed pole sitting there, and your contour get trapped there. So you get a singularity at that point. It's the same situation here. That's the fixed one, that's your contour, and you are going to get a singularity at this place. Okay, your contour is going to get trapped there. Your contour is going to get trapped at y equal to 0, which means your contour is going to have this issue at z equal to infinity. Okay, so if you analyze this thing in the z plane, you will see that this corresponds to your contour being dragged and becoming infinite. Okay, and then you develop this other possibility. So we have seen three things in this simple one variable case, that you may have an endpoint singularity which depends on your external momenta, right? Sorry, on the variable z, and then you could have pinching of contours, a pinching of contour by some singularities approaching it. In our case, it was a fixed one, but you could have two singularities which are migrating and pinching the contour, or you could have third case where the pinch happens at infinity, or the contour equivalently gets dragged to infinity.
So this pinch at infinity, can we just think of it in the same category as pinch singularity if we just say that infinity is just another point on the fixed plane?
Yeah, that
Nothing. Is there anything more to it than that?
this is it is happening at infinity. Yeah, that's the thing. So I'll stop here, and I think, and next time we will look at the case of Feynman integrals and try to find out. See, what will be your goal? Your goal will be, you have Feynman integrals which are functions of external momenta, p1, p2, whatever. That's the equivalent of z here. As you change the external momenta, where are the poles located and how they are moving around, and whether such a pinching happens. Because if a pinching happens for certain configurations, you will know that there is a singularity, and you want to know where are the singularities for the Feynman integrals, and you want to know all that because you are interested in knowing the infrared structure which is coming from all those singularities, and you are interested in that part because eventually you want to make predictions for observables where contributions coming from such configurations, infrared configurations, are the dominant ones, right, where you require a summation. So that will be the next thing we take up. Okay, thanks. If you have questions, you can ask. Okay.